About 2,000 years ago, during a time when human civilization was flourishing, humanity experienced its first era of prosperity in history, barely managing to escape a life of daily toil for daily sustenance. With this newfound leisure, some began to ponder, what have we been living so hard for? What has made our lives so difficult? What has brought us into such a challenging world? These questions snowballed and eventually shifted their focus to the essence of nature. This curiosity soon turned to the light that illuminated half of the day, and scholars researched the nature of light over centuries. During this process, some claimed that light was simply a natural phenomenon, or that light originated from our eyes because we could only observe objects when we opened our eyes, a notion that is incomprehensible today. However, in the 17th century, humanity began to research light more earnestly. Beyond seeing light as merely a divine presence, they sought to understand why light occurs, where it begins, its characteristics, properties, and everything about light. As a result, the hypotheses about light were narrowed down to two choices. One was the particle theory of light, which posited that light, like other materials, could be broken down into small particles. And the other was the wave theory of light, which suggested that light moved like a wave. The strange thing was that sometimes light behaved like particles, and at other times like waves. No one could refute the other, but neither could they admit they were wrong. Clearly, a substance should have only one property, and it was baffling to see mutually exclusive characteristics in one entity. Therefore, Isaac Newton, the father of classical mechanics, asserted the particle theory of light. Using a prism, he discovered that different refractive indices of light combined to form white light, and claimed that the light of different refractive indices was composed of the smallest particles of light, i.e., particles. With such definitive evidence, the wave theory of light lost ground, and the debate seemed to end in favor of the particle theory. Moreover, Newton, who had become a giant in the scientific community with his papers on universal gravitation, left most scientists unwilling to challenge his particle theory of light. However, in the early 19th century, a scholar who challenged Newton's authority emerged. Thomas Young, a British physician and physicist. To understand the nature of light, he devised an interesting experiment. He prepared a double slit with narrow gaps and passed light through it. If light were particles, it would pass through one of the two gaps. But if it were a wave, it would pass through both gaps and show an interference pattern, a characteristic of waves. The experiment showed that the light passing through the double slit displayed an interference pattern, one of the wave characteristics, replacing the long-standing particle theory of light with the wave theory of light. Furthermore, in the mid-19th century, James Clerk Maxwell, the father of thermodynamics, succeeded in calculating the speed of electromagnetic waves through his equations on electromagnetism, proving that light was also a type of electromagnetic wave. Thus, light, which began as particles by Newton, seemed to conclude as waves. In the early 20th century, however, the debate about light that had lasted for 300 years was settled by one scientist. He was Albert Einstein, the greatest physicist in human history. In 1905, Einstein astonished the world with his groundbreaking papers on the photoelectric effect, Brownian motion, and special relativity. Among them, his paper on the photoelectric effect suggested the astonishing idea that light could be both a particle and a wave. Until then, it was unimaginable that any object could have two properties. But it was impossible to explain the phenomena occurring in the world without assuming that the light we see, which we can easily observe even now, possessed both properties. Even more astonishing was that determining whether light was a particle or a wave was not done by a god or some transcendent being, but by any act of observation by humans, animals, plants, or any observer, fixing it into one property like magic. This soon led to the concept of matter waves, where particles like electrons could also have wave-like properties. As a result, quantum mechanics, a field that Einstein opposed all his life but ultimately became established successfully, was born. So, what does quantum mechanics tell us? What stories does it hide from us? Today, let's delve into the science of what is quantum mechanics, right now from our room. Around 400 BC, Greek scholars who were trying to explore the essence of the world thought that matter could be divided infinitely into smaller and smaller pieces. They believed that if you kept breaking down a rock, it would become pebbles, then sand, and continue to break down into unknown tiny particles. However, Democritus thought that if you kept breaking down matter, you would eventually reach tiny, indivisible particles. He named these smallest indivisible particles atoms. Thus, the concept of atoms, the smallest basic units of matter, was born. However, because atoms existed only in his imagination, the atomic theory of matter gradually faded from people's memories. Over 2,000 years later, in 1803, the British physicist John Dalton officially announced the atomic theory to the world. Dalton argued that all matter is made up of indivisible atoms, and that atoms of different kinds have different sizes and masses. Although there were many aspects to improve as it was the first theory, Dalton's atomic theory established the idea that the basic unit of matter is the atom. One of the most critical weaknesses of Dalton's atomic theory was that atoms, thought to be the smallest particles, contained other particles within them. In 1897, British physicist J. Thomson devised an experiment to uncover the true nature of atoms. By applying voltage across a vacuum tube called a Crookes tube, he attempted to separate atoms. Surprisingly, the experiment revealed that there was something new with a negative charge inside the atom, which he named the electron. This discovery shattered the notion of atoms being indivisible and shifted the focus to how atoms are structured, based on the fact that atoms contain positively charged protons and negatively charged electrons. Thomson proposed the first atomic model, which he described as a plum pudding model. In this model, electrons were scattered like raisins in a positively charged pudding. Thomson's model suggested that electrons were stationary, but they were actually free to move within the positive charge. For this achievement, Thomson was awarded the Nobel Prize in Physics. In 1911, Thomson's student Ernest Rutherford challenged his mentor's model. Through experiments, Rutherford discovered that positive charges were concentrated in a very small space within the atom. According to Thomson's model, electrons should be embedded in the positively charged protons. Contrary to this, Rutherford found a high-mass substance with concentrated positive charge. Consequently, Rutherford improved upon Thomson's model and proposed a new atomic model. This model depicted electrons orbiting around the nucleus, much like planets orbit the Sun. This model, which clearly illustrated the relationship between protons and electrons, remains useful in teaching students. However, Rutherford's model had a critical flaw. Magnets show that positive and negative charges attract each other strongly. Therefore, the positive nucleus and negative electrons should attract each other and collapse. According to Rutherford's model, electrons orbit the nucleus without being pulled in. This implies that the electrons use energy to maintain their distance, raising the question of where this energy comes from. If electrons are maintaining their orbits this way, Maxwell's wave equations predict a dire outcome. Electrons in rotational motion emit electromagnetic waves, losing energy in the process. Eventually, the electrons would lose enough energy to spiral into the nucleus, causing the atom to collapse. This would mean everything in the universe, including our bodies, Earth, and the Sun, would eventually disintegrate. Thankfully, such events are not happening around us. Although Rutherford's model was more sophisticated than Thomson's and explained many physical phenomena, it couldn't explain why atoms maintained their orbits. At this time, one of Rutherford's students approached the problem in an unexpected way. That student was Niels Bohr, the father of quantum mechanics. Believing Rutherford's model wasn't wrong, Bohr sought to find why atoms didn't collapse instead of proposing a new model. He theorized that electrons in stable states didn't emit energy and thus maintained their orbits. Bohr suggested that electrons could only exist in specific orbits and couldn't exist between them. Astonishingly, Bohr proposed that when electrons change orbits, they do so instantaneously without passing through the space in between. For example, a planet orbiting the Sun could instantaneously move to Mars' orbit and then to Neptune's orbit. This idea was hard to accept because objects in our everyday world move through the space between points A and B, not by instantaneous jumps. Although Bohr's third atomic model perfectly explained the mysterious phenomena of the quantum world, its inability to explain the reasons behind it made it a target for many scientists. During this period, the secret of electrons, which seemed unsolvable, was resolved by chance. The atomic model was a hot topic in the scientific community, and French scientist Louis de Broglie delved into the problem. However, conventional wisdom couldn't explain these phenomena. While taking a break with fellow scientists, de Broglie recalled a groundbreaking idea from Einstein's paper on the photoelectric effect. which suggested that light could be both a particle and a wave. Inspired, de Broglie hypothesized that electrons could also be both particles and waves. He further developed this idea into the concept of matter waves, significantly altering the course of history. Unfortunately, de Broglie's groundbreaking paper didn't receive much attention from other scientists, except for one, Einstein. Einstein, impressed by de Broglie's genius, introduced the paper to his colleagues and worked to refine de Broglie's matter wave theory. By using the matter wave, we could explain the stationary states and quantum jumps in Bohr's atomic model, which had not been explained before, and also explain the wave nature of all substances other than hydrogen. However, there was a clear limitation to de Broglie's matter wave theory, whether electrons really have both particle and wave properties at the same time. If matter truly has both particle and wave states, it might be a bit mind-boggling, but it would solve all the unexplained phenomena so far. The problem was how to prove that particles have both states. But this problem was surprisingly easily solved. Just 3 years after the matter wave theory was announced, in 1927, Clinton Davison and Lester Germer, who were working at Bell Labs at the time, proved the matter wave theory through an experiment, inspired by Thomas Young's double-slit experiment, which demonstrated the wave nature of light. They conducted an experiment under the same conditions, but fired electrons instead of light. Believing that electrons were particles, they thought that some electrons would hit the wall and bounce off, and some would choose one of the two holes and reach the screen behind the wall. However, the experimental results were unexpected. According to our expectations that light is a particle, two stripes should have formed on the screen behind the two holes where the electrons passed. But instead of two stripes, multiple stripes appeared. In other words, the electrons we firmly believed to be particles also had wave properties. Thus, the Davison-Germer experiment proved de Broglie's matter wave, showing that matter is both a particle and a wave. However, this only added more confusion for scientists. While the theory explained everything, it was difficult to express these phenomena mathematically. At this point, another savior appeared, Heisenberg, a student of Sommerfeld who was working with Bohr at the time. Heisenberg studied under Bohr for about 8 months, listening to all his explanations about atoms, and decided to mathematically describe the phenomena that all scholars were struggling with. However, converting the movement of atoms into mathematical formulas without even knowing how they move was not easy. To describe the motion of a substance using classical mechanics, one needs to know exactly where the substance is located and its state, meaning the direction and speed of its movement. The problem was that it was impossible to know the position and speed of an atom. While ordinary scholars might think this was simply because observation equipment was not advanced enough, Heisenberg instinctively thought it was impossible to know both position and speed simultaneously. But he did not intend to create a theory based on vague guesses. Fortunately, there was one clear indicator we could directly see: the light emitted by atoms. As we learned before, electrons orbiting the nucleus are located in specific orbits. They cannot be positioned between orbits. When an electron makes a quantum leap from one orbit to another, it emits energy, and hydrogen emits specific light during these transitions. For example, moving from the second orbit to the first emits red light, and from the third orbit to the first emits blue light. Using this, Heisenberg could know the approximate physical quantities of an atom, and he succeeded in mathematically explaining Bohr's atomic model using a complex method called matrix mechanics. His matrix mechanics, which made it possible to systematically analyze the previously imaginary atomic model, deserved praise from many scientists. However, a scientist who did not like Heisenberg's matrix mechanics was none other than Albert Einstein. Einstein did not like Heisenberg's matrix mechanics, which was composed of numerous formulas and numbers. When Einstein, who had enormous influence in the scientific community at the time, showed a negative reaction, the scientific community naturally began to ignore Heisenberg's great achievement. Moreover, a scientist, seeing Heisenberg's matrix mechanics, called it a meaningless array of numbers, and, within just 1 year, announced an equation to explain the atomic model. That was Schrödinger's wave equation. Unlike Heisenberg, who assumed electrons were particles, Schrödinger assumed electrons were waves and mathematically described how these waves move. According to this wave equation, the probability of finding an electron at a specific location at a specific time could be calculated. Moreover, unlike the complex and difficult matrix mechanics, Schrödinger's wave equation was relatively easy and visually expressive, gaining support from Einstein and the great scientists of the time, pushing Heisenberg's matrix mechanics to the background. However, his wave equation only allowed for the probability of an approximate position, not the exact location and velocity of an electron. Once, Schrödinger held a seminar, and Heisenberg, insisting that the wave equation was useless without knowing the electron's position and momentum, shouted that his matrix mechanics were correct, leading to his expulsion from the seminar. Afterward, Schrödinger and Heisenberg became arch-enemies, and scientists supporting each of them split into two factions. This soon escalated into one of the greatest conflicts in the scientific community. Shortly after the clash, Heisenberg was offered a university professorship at the young age of 24, but he turned down the position to continue researching atoms in Copenhagen, Denmark. It was then that a thought struck him. Why can't we know the position and velocity of an atom simultaneously? Why can't we see both at the same time? What does it mean to observe? Observing something means that light collides with an object, and we receive the reflected light. Most materials around us are hardly affected by light. But what about extremely tiny particles like atoms? Simply put, to observe something, light must be shown on it. Atoms are so small that even light can change their position and velocity. Therefore, when illuminated with long wavelength light, which has relatively low energy, an atom's momentum can be determined, but its position cannot be pinpointed accurately. Conversely, when illuminated with short wavelength light, which has high energy, the position can be determined accurately, but the atom absorbs the energy, making its velocity difficult to measure. Baffled by this phenomenon, Heisenberg sought advice from the greatest physicist of the time, Einstein, but found his response unsatisfactory. Just because we can't directly observe an electron doesn't mean we can't know its position or velocity. That's an overreach. With time and advancements in observational equipment, we will be able to measure both the position and velocity of an atom. Putting aside the development of observational equipment, Heisenberg, unable to base his theories on unobserved phenomena, returned to his laboratory to try every means to observe both quantities simultaneously. However, no matter what methods he used, it was impossible to obtain both physical quantities simultaneously. Eventually, Heisenberg wrote a paper about this. This paper, known as the cornerstone of modern quantum mechanics, is the uncertainty principle. The uncertainty principle, in simple terms, states that measuring a particle's position means its momentum cannot be known, and measuring a particle's momentum means its position cannot be known. This is a fundamental characteristic of particles. So, contrary to Einstein's advice, no matter how advanced measurement equipment and technology become, the position and velocity of a particle cannot be measured simultaneously with accuracy. But this did not answer the question of whether Heisenberg's matrix mechanics or Schrödinger's wave equation was correct. Interestingly, although the premises and mathematical approaches of matrix mechanics and wave equations were entirely different, their calculation results were identical. Heisenberg's mentor, Bohr, then made a shocking statement to him. Einstein had shown that light is both a particle and a wave, and de Broglie had shown that even matter is both a particle and a wave. So, why should it be surprising that there are two ways to explain a phenomenon? In other words, Heisenberg's matrix mechanics and Schrödinger's wave equation were both correct, and they simply needed to be applied according to the situation. Initially, Heisenberg could not accept his mentor's claim, but he found no flaws in it. Eventually, he accepted it, and since they were in Copenhagen when they interpreted this, it is now known as the Copenhagen interpretation. In the 21st century, to explain what happens in the quantum world, there are interpretations like the Copenhagen interpretation, hidden variable theory, many worlds interpretation, and even the soul interpretation. However, the interpretation most accepted by scientists is the Copenhagen interpretation proposed by Niels Bohr and Heisenberg. But the Copenhagen interpretation faced numerous challenges, the greatest being the opposition from the greatest physicist of the time, Einstein. Schrödinger, who had worked with Einstein on the wave equation, claimed they hadn't reached a definitive conclusion and used various examples to argue that their interpretation was wrong. Then, one day, a great opportunity arose to determine whether Einstein's classical mechanics or Bohr and Heisenberg's newly developed quantum mechanics was correct. This was at the Fifth Solvay Conference on Physics in 1927. Here, many of the greatest physicists of the 20th century participated, and the topic, unfortunately, was electrons and photons. At this conference, Einstein's classical mechanics and Bohr's quantum mechanics fiercely clashed. The next science topic we'll explore in Science from the Couch is why Einstein denied quantum mechanics. This has been Science from the Couch. Thank you.